let's talk about Rouché's theorem, which is again a theorem about counting zeros. And this one is slightly different. This one is basically saying that if one function is sufficiently close to another function, then it has the same number of zeros, or say numbers of 0 minus poles. So what do we mean by close? So if we have two holomorphic functions, then we think that they're, at least for the purposes of this theorem, that they're close on a cycle. And so this is going to be uniformly in the uniform metric, for example. So we're going to take the supremum of their difference, really, is the close, how close they are. And we're just going to look at a cycle, and basically we then look at what's inside the cycle. And as long as they're close on the cycle, then the number of zeros are going to be the same inside. It's going to have the same number of zeros. Maybe they'll move around a little bit. Maybe one of them has a zero of multiplicity 2, the other one has two distinct zeros. Well, that's fine, but they're going to have the same number of zeros up to multiplicity. More generally, if we have meromorphic functions, then it's the number of zeros minus the number of poles. Now let's look at the example for holomorphic functions, which is really if we have, let's say, it's z squared and z minus epsilon, z plus epsilon. Suppose that epsilon is small, then well, they both have really two zeros up to multiplicity. One of them, they're both 0, and one of them is has 0 at minus epsilon and plus epsilon. And both of these functions are actually close on the unit circle. And so basically what this the Rouché's theorem is going to say, well, then it has to be something like this. If they're close on the unit circle, they're going to have the same number of zeros. For meromorphic functions, to be a little bit careful, zeros and poles sort of cancel one another. So for example, the constant function 1 and the function z minus epsilon divided by z plus epsilon, which has a 0 at epsilon and a pole at minus epsilon, those two functions are close on the unit circle. So they're maybe let me go back to this. So basically, one of them has no zeros, no poles, and one of them has 1 0 and 1 pole, and that's the same. If we do this subtraction, the number of zeros minus the number of poles, we get the same integer, right? So that's what this term, what Rouché's theorem is going to count, right? So here is Rouché's theorem. Suppose that we have almost as usual now. Suppose we have an open set, and we have a cycle in U that is homologous to 0 in U. So again, it doesn't go around anything that's not in U. So it doesn't go around anything in the complement of U. Now, let's suppose, this is, they talked about this last time, let's suppose that gamma really doesn't go around any point more than once. It goes around some points once, and it just doesn't go around some other points, right? And so let's, so now we can have a nice definition of what's inside gamma. Well, it's all those points that gamma only goes around once. So that's the inside of gamma. Now, let's suppose that we have two functions, and let's just suppose right now meromorphic. There's going to be there's a simpler version of for holomorphic functions. So let's suppose that we have two meromorphic functions, f and g, And let's suppose that they have no 0, 0 poles on gamma, and suppose that on gamma, for all z on gamma, we have this inequality, that their difference is strictly less, then it has to be strict inequality, strictly less than the modulus f plus the modulus of z. All right. I'm sorry. Now, if we take if we let n sub f and n sub g be the number of zeros in V of f and g, and pf and pg are the number of poles of f and g, then what we get is that these differences, n sub f minus p sub f, is equal to n sub g minus p sub g, right? The number of poles, number of zeros minus number of poles is equal to the number of zeros minus the number of poles of both functions, right? So as long as they satisfy this inequality over here, right? Now let's look at a simpler version for just holomorphic functions. Suppose that we have suppose u, gamma, and v are as in this theorem, and suppose that f and g are actually holomorphic now on u. And again, we get the same inequality. Now, over here, notice that we didn't say that there are no zeros on gamma, and it's fine, because if there are, this cannot be satisfied. So, for example, if g had a 0 on gamma, then you can see that I cannot have this strict inequality satisfied, right? So as long as you have this strict inequality, you know that you automatically don't have any zeros on there. And then f and g have the same number of zeros in V, in this inside of gamma, up to multiplicity, of course. Now, the classical statement of the theorem uses a slightly weaker inequality. It's basically we sort of forget about the g on the right hand side, and we just have that f minus g is less than the modulus of f. Now this has a very nice geometric interpretation, and this is sort of the geometric proof of this theorem, and it's where you're walking a dog, and so the master of the dog, right, is he's going to be our f. So as z moves around some gamma, the master will go around 0 some number of times, and that's what counts the number of zeros of f. Let's just suppose that we're holomorphic. Everything's holomorphic, right? So it's the number of times that the master goes around the tree. That's the number of times that f is 0 inside gamma. Now, g is a function which is nearby. Let's just say it's a dog, right? And the dog can sort of run around the master, but the dog is on a leash, right? Now, the length of the leash is the difference between, well, the modulus of the difference of these two functions. And so, as long as the leash is never longer than the distance from the master to the tree, well, then the dog couldn't have gone around the tree more or less times than the master could have, right? If the master goes around 3 times, then and as long as the leash is never longer than the distance from the master to the tree, and that's precisely this is inequality. It's this side, that's the length of the leash, and over here is the distance from the master to the tree. So then the dog, if this is always satisfied, if the master went around 3 times, the dog went around 3 times. And so if f has 3 zeros, so does g. So this is a sort of a nice geometric interpretation of what this inequality is. If we're thinking of this thing is of these ideas as sort of in this argument principle sort of way. All right. So let's look at the proof of this theorem. Let's rewrite the inequality as follows. So that's just a little bit of algebra, and we look at the function f over g. Let's call it phi, just so that we don't have to keep rewriting it, and the formula later on will become a little nasty. Let's write this function phi, and notice that this inequality, what it says is that this phi is never positive on gamma. It's also never zero, of course, but it's never positive. So let L be a branch of the logarithm on this slit plane, on the plane that is the plane minus zero, the non-negative real numbers. Well, the function phi prime divided by phi, well, that has an antiderivative. Well, it's really the log of phi, right? And so it's L composed with phi. But this this is a well-defined antiderivative in a whole neighborhood of gamma, right? Because phi is never non-negative. It's never zero. It's never positive. So that means that I can I can plug it into L, those are the values where L is not defined, right? So that means by Cauchy's theorem for derivatives that this integral of phi prime over phi around gamma is just 0, right? Well, and if that's 0 on one hand, then if we compute what that is, if you just do, and this is really just putting putting your quotient rule to work, you will actually get that phi prime over phi is equal to f prime over f minus g prime over g. And once we're there, then it's just argument principle to finish the proof, right? I mean, we basically have that the integral from argument principle for f and for g, that those two are the same, right? So that's the proof. Now let's look at an application. And so this is a sort of a typical application of the simplest typical application of Rouché that is usually used to sort of demonstrate the theorem, is to again locate zeros. Now here we don't have to compute an integral; we just have to show a certain inequality. So let's show that this function, this polynomial p, which is z to the n minus 1. Well, we know how to solve this, but well, let's suppose that we didn't. Let's show that all its zeros are on the unit disk. So we know it has n zeros, but maybe we don't know what they are. Right? Let's use this term. This is a toy example. We're going to use. We're going to look at a slightly more complicated example in a bit, but let's do this one first. So first, if I look at a circle of radius slightly less, so let epsilon be some small positive number. So a circle of radius 1 minus epsilon around 0. Then on this circle, so when mod z is slightly less than 1, then if I take p minus 1, so it's going to be p is going to be the dog and 1 is going to be the master, then p minus 1 is just z to the n, right? The modulus of this is the modulus of z to the n, and since z is strictly less than 1 on this circle, the modulus of z is strictly less than 1 on this circle, well, this is strictly less than 1. So, and 1 is precisely, that's the modulus of f, of the master, right? So we have that p, the polynomial p and the constant function 1 has the same number of zeros in this disk of radius 1 minus epsilon, which means there are no zeros there, right? There is no zeros in an arbitrary size disk for any epsilon, so all the way up to 1, right? There are no zeros there. On the other hand, if I look at a circle that's of slightly bigger radius, 1 plus epsilon, than the unit circle, well then let's subtract z to the n. So p of z minus z to the n, well that's just 1, right? And if we're on this circle, then modulus of z to the n, well, is just the modulus of z to the nth power that is strictly bigger than 1. So therefore now we have something slightly different. We have that z to the n and p have the same number of zeros in a disk of radius 1 plus epsilon. Now both of these statements were true for an arbitrary epsilon, and therefore all the zeros, we know that there are n zeros, they have to be on the circle, right? Okay, let's look at a slightly more complicated example. Suppose that p is this complicated polynomial, and let's try to, maybe let's not try to find the exact zeros, but let's try to at least locate them to some degree, get some handle on where could they possibly be, without actually trying to compute them. So for example here, I could subtract z to the 4th plus 24 z squared, and if I do that, if I subtract that from p, I get this expression, and well, I could just apply the triangle inequality, and I get this expression. Now, when I'm looking on the unit circle, when modulus of z is 1, well, I get, I can compute what this is precisely, because modulus of z is 1, so this is 12, this is 4, this is 6, so I get 22, right? Now 22 is strictly less than 23, right? And 23, well, that's precisely equal to this this expression over here. The modulus of 24 z squared, because we're on the unit disk, so that's just 24 and minus modulus of z to the fourth, and again we're on the unit disk, so that's just 1. So this is 23. And by the inverse triangle inequality, we get that it's modulus of z to the fourth plus 24 z squared, which happens to be that's the thing over here that we subtracted, right? So that means that z to the fourth plus 24 z squared have the same number of zeros inside D as P. Now, this simpler polynomial z to the fourth plus 24 z squared that is easy to factor. It has a couple of zeros at square root of 24 times I plus minus, and those are outside D. But it also has 2 zeros at the origin, because I can factor out z squared. So P has to have 2 zeros, well, maybe not at the origin, but it has 2 zeros in the unit disk, right? Okay, so let's try to figure out something more about this, where these zeros are. We know that 2 of them are in the unit disk. So let's look at a circle of radius 46 plus epsilon, so slightly bigger than 46. And now let's subtract z to the fourth. So z to the fourth has 4 zeros at the origin. So inside this disk of radius 46 plus epsilon, and it has the same degree as P. So if we find that it has the same, all the zeros of P are in this disk, which we will, then those are all the zeros of P, right? So if we do this subtraction, we get this expression over here, and we're just gonna estimate it in the simplest possible way. We know that mod z is bigger than 1, so we apply triangle inequality, and then we just multiply by the right part of mod z to get all the parts to be 3. So this is a fairly rough estimate over here, but it works. And then since mod z is bigger than 46, then we get this estimate over here, and that's a strict estimate, and that's just the modulus of z to the fourth. So therefore, we have that all zeros are in this disk for any epsilon. So really, all zeros satisfy this non-strict inequality. They're all of modulus less than or equal to 46. Now this is actually not the ideal estimate. There are we actually, if you'd actually compute all the zeros, you'd find out that none of them have modulus more than 10. But that's that's not the point here. The point here is to get some sort of handle on it, and we really did a very rough estimate. The better estimate you do, the more handle on the location of these zeros you get. Right. So these are sort of classical examples of Rouché theorem, but Rouché theorem is really about how does the number of zeros, or perhaps poles, change when you change the function a little bit, and basically it says they don't change. If I have a holomorphic function, then basically what it says is that if I change the function a little bit, then the zeros cannot disappear, or new ones cannot appear. They can at best maybe move a little bit, right? move a little bit inside the inside gamma. All right.